Yeah, so it's basically about 3D generation. So it's the first model that can do feed-forward text to 3D generation in under a minute. The basic idea is to first use a 2D diffusion model to generate multiple views of a 3D asset, and then use a feed-forward kind of NeRF reconstruction model to generate the 3D asset from the multiple view input.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, a podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper Instant3D, Fast Text to 3D with Sparse-View generation and large reconstruction model. This paper was accepted to ICLR 2024, and I am happy to host the first author of the paper, Jiahao Li. Hello and welcome to the podcast. Can you introduce yourself?
Yes, hi, Isaac. Thanks for having me. So my name is Jiahao, and I'm a fourth-year PhD student at TTIC, which is a research institute on the campus of the University of Chicago. So my main research area is generative models and 3D computer vision. And in the past summer, I did an internship at Adobe, mentored by SciB, and we worked on some like 3D generation stuff, and we had a paper about feed-forward 3D generation on ICLR this year.
Wow, it always amazes me how these internships can become like these great projects and paper that make it out to the world.
Exactly. They have abundant resources. Yeah.
Yeah. So tell me, who are the co-authors of the paper?
Yeah, co-authors are mainly people from Adobe, Hao Tan and Kai Zhang, Zexiang, Fu Jun. They're all like, and SciB, they're all like full-time workers. And there are two other interns that also contribute to the paper, Ying Hao and Yi Cong. Yi Cong has actually become like a full-time employee at Adobe this year. And also Kalian, which is the manager of us all, and Greg, my advisor. Yeah, co-authors.
Yeah, quite a list of co-authors. I actually know Itsong, and he was here on the podcast when he was still doing his PhD at the Australian National Institute. That's where I know him from.
Yeah.
I spent some time there as well. Okay, but let's talk about the paper now. I'm super excited to get started. So in a TLDR kind of format, what is this paper about?
Yeah, so it's mainly about text to 3D generation. So previously, text to 3D generation are heavily based on test time optimization. So given a text prompt, we need to optimize a NeRF on the fly with guidance from 2D diffusion models. But that would be very slow. For state-of-the-art models, we usually need hours to generate one 3D asset. So our paper aims to accelerate that process without significantly kind of degrading the quality of this generated asset. So the basic idea is that we found that after some fine tuning with like a small amount of 3D data, a 2D diffusion model can actually generate multiple view images of the same asset based on text in a very 3D consistent manner. So that we first use 2D diffusion model to generate a sparse set of multiple views of the same object. And then we train a transformer-based 3D reconstruction model that reconstructs the NeRF model from the generated sparse multiple views. So that would give us like a fully feed-forward model that without test time optimization can generate very high quality 3D asset from text prompts.
This is so cool. Like doing this in I think it's around 20 seconds per shape, like compared to what was previously state of the art, which is like, I don't know, 10 hours or even 1 hour. That's a huge boost in speed. And I can't wait to dive deep into how you guys did it and how you kind of curated the data and how you trained everything. But before we do that, let's kind of spend some time talking a little bit about the problem and like to people that don't know this space. So what are the challenges in this domain? So what makes this problem interesting and difficult to solve?
Yes. So text to 3D generation by definition is like given a text prompt, we generate a 3D asset in some format like meshes or NeRFs, neural radiance views. So the main challenge is data. So we now see this like success of 2D diffusion models that can generate like high quality realistic images. They rely on training on a large amount of 2D data, and 2D images are like very easy to obtain from the internet. But 3D data is very difficult to get because it usually requires like heavy human labor to manually construct these like 3D geometries and add textures. So we cannot use the same technique as 2D generative models to just apply it to 3D generation. So in 2023, I guess. So there's this paper from Google called Diffusion. It basically utilizes a 2D diffusion model to kind of distill the information of a 2D diffusion model into a 3D representation, which is a NeRF. So that process can kind of uses the semantic kind of generation capability of a pre-trained 2D diffusion model, but still generate 3D asset. So that's like the uses an optimization procedure in their method. So it takes like hours on maybe multiple GPUs to generate one shape from text. And another main challenge is called the Janus problem, because we're not training a model to generate 3D assets. We're just distilling 2D information into a 3D representation. Usually the end 3D result, will not look like a normal shape, but it will look like a shape that have multiple like faces stitched together to maximize the kind of the distillation objective. And it looks good to the model. It has like low loss, but it does not look good to humans. Yeah, we can see a lot of these kind of examples, maybe in our paper or in the Diffusion paper. So these are the main challenges. These are the two main challenges: the data scarcity and the Janus problem, I guess.
Yeah, I think it's really interesting that one of the challenges that keeps repeating itself with every paper that came out in 3D is that we just don't have the same amount of data in 3D that we do in 2D or by far text, right?
Yeah.
And here in this case, we're actually trying to generate an image, right? Sorry, not an image, a 3D shape, right? So you get
Yeah.
a text prompt and you're trying to create this 3D shape. You're going to need a lot of data to train that from scratch, and we just don't have that. So you kind of have to find creative solutions like you guys did to cope with that. But okay, so we got the challenges covered pretty well. But what are the main contributions of this paper then?
I guess the main insight from the paper is that we discover that with by fine tuning a pre-trained 2D diffusion model with a relatively small amount of 3D data, which is around 10K in our paper, we can use it to generate a sparse set of views of the same 3D object. And these views are actually very 3D consistent. And I think this is surprising because the 2D diffusion model is trained in a completely 3D agnostic way. So, and there is no internal structure of the 2D diffusion model to kind of enforce 3D consistency. And previously, there was a paper called 0123 that showcases the ability of the 2D diffusion model to generate multiple views with a condition on one single view. But the results are not strictly 3D consistent. They basically need to use techniques from like diffusion or SJC, our previous paper, to kind of still do optimization on the 3D representation to enforce the 3D consistency. But in our paper, we find that we can fine tune it to directly generate very 3D consistent multiple views. And so we can also use a feed-forward 3D reconstructor model to directly reconstruct a 3D asset from the set of views, the set of generated views. If these views are not 3D consistent, we cannot do that. We need to do optimization to eliminate those inconsistencies. But now we have this almost perfectly consistent input images. We can train this like Sparse-View 3D reconstruction model to do a feed-forward reconstruction. So these two parts, the view generation part and the feed-forward 3D reconstruction part, forms the entire pipeline of a model and makes it completely feed-forward, so we can generate things like in under 20 seconds.
Wow, yeah, I find it fascinating, I have to say. Like, when I first read the paper, I was thinking exactly what you just said. Like, the 2D image generation part is not in any way supervised by the 3D part, right? And you still manage to produce these very consistent multi-view, like very sparse multi-view observations that basically allow you to create these 3D objects. And I can't wait to dive more into the details of that. But before we do, let's talk a little bit about related work, right? So if someone is just starting out their PhD, they're super excited about generative models for 3D asset generation, and they want to start somewhere, they come to read your paper, and what would you recommend them to read in order to understand things better and get like this in-depth comprehension of the field?
Yeah, I think there are three main categories of method in 3D generation before this work. So the first category is not text to 3D, but just 3D generation. Is usually trains on like a smaller data set like ShapeNet, which has like less than 100 categories of objects. And I don't have particular recommendation for those papers because it's not text to 3D. It's not directly related to our paper. But for text to 3D, there are two main categories. One is mainly done by OpenAI, which consists of I don't remember the previous model, but the latest model is called ShapeE. It basically kind of trains a 3D diffusion model on a large amount of 3D data. And there's this like famous data set called Observers. I'm not sure if they use this data set in their model, but internally they have another very big data set. And I think this is one of the models we compared to. And the other more important category is what I just mentioned, optimization-based methods, which kind of uses a pre-trained 2D diffusion model to generate 3D assets. The most important paper is called Diffusion from Google, and there are a lot of follow-up works. And I think the state of the art is called Prolific Dreamer, which kind of solves some of the problems of dream fusion, including like low diversity and kind of flat textures and things like that. So I think Dream Fusion and Prolific Dreamer, these are the two most important papers in this optimization-based category. Yes.
Yeah, totally. I'll make sure to put links to these papers in the episode's description. Let's dive into the approach. So what did you do and how did you do it?
Yeah, so there are two parts our pipeline has two parts. The first part is Sparse-View generation, and the second part is 3D reconstruction. So for the Sparse-View reconstruction, we basically fine-tune a 2D diffusion, pre-trained 2D diffusion model, which is Stable Diffusion. In our paper, Stable Diffusion XL actually, and we fine-tune it using a small amount of high-quality 3D data. We use this. We filter the object-verse data set, which consists of around 800K 3D assets. We hand label like 2,000 random shapes from the data set as good or bad. It's completely subjective, and then we train a small kind of classifier and SVM to classify the shapes into kind of good or bad, and we sort the entire data set by this metric and get the top 10K most high quality training data. And then we use these kind of high quality training data to kind of fine tune the 2D diffusion model. And because we need to generate multiple views of an object, so we need to, but the original 2D diffusion model just generate one image. So there are some other works that kind of modify the structure of the 2D diffusion model to generate multiple views. But since our idea is just to prove that we can generate 3D consistent multiple views from 2D diffusion model, so we want to use the kind of simplest approach to do that. So basically, we kind of divide a single image canvas into like quadrants, so that we have 4 sub images in one image. So the resolution of Stable Diffusion XL is like 1024 by 1024. So we divide it into 4 images. It would be 512 for each image, and then we can construct training images that consist of these quadrants of images, quadrants of multiple views, and use that as one single image to fine-tune the 2D diffusion model. So that's like the simplest approach we can think of, and it does not require any kind of change to the network architecture, and we don't need to change the kind of training procedure. We just use the same kind of fine-tuning procedure for diffusion models as those like 2D fine-tuning for 2D images. So after this fine-tuning, we can basically, given a text prompt, we can generate a image of quadrants, 4 sub-images, and each image will be like a view of an object from a fixed pose. So given these 4 images, we basically want to, so this part is completely feed-forward, and it takes the same time as 2D generation from a diffusion model. So now we want another feed-forward method to generate the 3D asset, which is in the representation of NeRF from these 4 images. So there's another paper by Adobe called a large reconstruction model, and our second part of the pipeline is based on that paper. So in that paper, they basically kind of do a single image to 3D generation using a transformer architecture. So the final results are in the form of a triplane, which is like a popular representation of NeRF when you want to output a NeRF in a feed-forward network architecture. And so the idea is very simple. We just use a transformer, and we divide the input images into patches and concatenate them all together, and use a transformer-based model to output like kind of great features of a triplane model, and then supervise the model with like novel views to make sure that it generates like 3D consistent assets.
Mm-hmm. Yeah. Okay. So this is a bit much. So let's try to break it down a little bit for the listeners. So the first part, it's generally subdivided into two parts, right? There's the completely 2D part, right, where you take a SDXL, Stable Diffusion XL model, and you generate these 4 views, right? Then you and the 4 views are generated in one go, right? It's 4 quadrant 4 quadrants. You generate them through the Stable Diffusion pipeline. Then you take
Yes.
each one of these quadrants, you feed that into another network that kind of encodes that into this vector that you're going to then use to, like in a cross attention kind of mechanism, to kind of condition the generation of the 3D object. Is that correct? What I just said,
Yeah.
or
Yes. Yes.
right? So once you have this vector, you now can like generate this 3-plane representation that you can create the NeRF out of, and you train that using. Oh well, we haven't talked about how you train that, right? So what do you optimize for? What's the loss?
Yes. So assume that we have a bunch of 3D data. So for each 3D shape, we can render a bunch of different views. And during training, because our end goal is to generate tripling from 4 input images, so for each shape during training, we randomly select 4 render images, and we feed that render images into the transport architecture and get a triplane. And then we randomly pick another image, another render image from the same for the same shape, but different from the input views. And then we kind of apply supervision on. We kind of apply supervision to force the rendering from the triplane to be basically the same as the ground truth view.
So it's this kind of a
That's the basic
reconstruction
idea.
loss, right? You
Yes,
compute
yes,
the difference between the generated image and the original ground truth image that you can basically generate from the original shape.
yes. So it's a completely deterministic model. And the probabilistic generation part is completely determined by the 2D diffusion part.
Mm-hmm. Yeah, and we should maybe talk a little bit about that, because you use this kind of a cool initialization there to like you're not starting from random noise as accustomed in most diffusion models. You're doing like this blob kind of Gaussian distribution kind of noise. Can you talk a little bit about that?
Yes. So yeah. So basically, if because we're fine tuning an existing 2D diffusion model, and previous the original model basically generate uh, a one single 2D image. So the kind of most common layout is that there's this one single object at the center, and there is some background. And we now want to fine tune it to generate quadrant images of quadrants. And we also want the background to be white so that we can eliminate the effect of the background when we're doing 3D reconstruction. And uh, also, when we fine tune the model, we want to kind of preserve the kind of the semantic capability of the original model. We don't want to destroy the weights too much so that it loses its understanding of text prompts. And so we can't fine tune too hard. But the thing is, like, if we directly use the random noise as initialization during the inference of diffusion model, it usually generates like images with some clutter background, because like we cannot completely eliminate its memory of the original model. So that it still tends to generate images with backgrounds, and sometimes it even fails to generate like images of quadrants. And so the way we deal with that is that we kind of uh, use a technique called SD edit. So basically, what SD edit does is that we during diffusion inference, we start from some image and add some noise to it, and it's not complete. Like the noise level is adjust it to some level so that it does not completely override the original image content. And then we use that as the initial point in the inference process and generate an image. So a notable example is we can use a segmentation image, kind of describing the layout of an indoor scene, and then we add some noise to it, do a diffusion process, and then we get an realistic image of a room, something like that. So this kind of technique can kind of encourage the model to generate images that conform to some initial layout that we specify. So because we want to generate images of of quadrants, we then initialize, as an initial point, we use an image with white background, but 3 black Gaussian blobs at the center. So this will, and then we add some noise to it and do the usual diffusion process. This will give a bias to the kind of the inference algorithm that we want to generate something that have 4 objects in the image, and they should have white background. Yes.
Yeah, this is such a nice idea because the problem with those diffusion models is that it can basically generate everything, and because you really care about consistency across the views. So if you now get a background, even if you get the quadrant, which is a problem on its own, if you get a background, there's nothing that kind of guarantees that it's going to be consistent across the views and may just cause random problems. So this solution, it was really nice to see how that works. So we have the quadrants, we feed that into the network, we get the vector, we feed that to the cross attention model, we get the tree plane representation, get the NeRF from that, train that using a reconstruction kind of loss, and there we have it. It all works perfectly. Now, in this kind of domain, let's move on to the results section. So in this domain, how do you even begin to evaluate the performance of this method?
So we basically evaluate it by eyes, by human eyes. So there is no kind of widely accepted evaluation metric for 3D generation. It is a hard problem, and we use clip scores in our paper, which basically evaluates the clip similarity between render views from the generated 3D asset and the text prompt. So this can evaluate the kind of the semantic consistency of the generated 3D asset and the text prompt, but it does not give any information about the quality of the 3D asset. So an example is the Janus problem, where we have multiple faces, that kind of multiple forward faces of an object stitched together to form a 3D model. But it usually has like very high clip scores because viewing from different angles, you always see like the face of a squirrel or the face of a human or something like that. But as a 3D asset, it's basically when we look at it in a turntable video, it's basically unacceptable. So I don't think I think there are some new papers that try to do 3D evaluation, but I haven't read them yet. So basically what we do is just generate a large amount of results and let the readers to decide which one is good or bad. In the supplementary material of the ICLR submission, which is on open review, so everyone can have access to that. We generate around I think it's around 200 or 300 or 400 hundreds of examples for our method, and also the other popular methods like Dream Fusion and Prolific Dreamer and Shape-E. And we kind of put all these results, the renderings of all these results in the supplementary material so that people can look at it and judge which one is better. Yeah.
Yeah, in this competitive field that we're in, right, there's always the question, was it cherry picked or wasn't it cherry picked? And I think this is a great example where you said, okay, there's no doubt this is not cherry picked. Here's 200 examples. You decide.
Exactly. Yeah.
Yeah, this is great. But were there kind of any, fail cases that you noticed that are kind of particular or stood out, or like unique cases that the method kind of failed on?
Yes. So there are some I would not call failure cases, but it sometimes generates poor quality results. And so in our final model, like the results are usually very good. But in our early experiments, when we do not do the data curation, for example, we use the entire Optiverse dataset to fine tune the model, it usually generates flat textures because there are a lot of bad kind of a lot of data in an Optiverse dataset with very flat texture or even no texture and or
Mhm.
very simple geometry. So if we fine tune the 2D diffusion model with this kind of uh, data, it will quickly adapt to that domain and try to generate flat texture or simple geometry, like a cartoonish. If you want to generate a pig wearing a backpack or something like that, it would generate a very cartoonish pig instead of like a realistic pig. So this is like one of the early failures that we observe. And um, we actually do not observe a lot of kind of failures in 3D consistency, which is very surprising because we generate multiple views using a complete like the diffusion model, which is completely 2D. But yeah, when it fails, it usually generates uh, kind of shapes that are consistent, 3D consistent, but they're not very consistent with with a text, or they're kind of have like very flat textures or geometry. So after we do the data curation, we this problem is alleviated, but it still exists to some point, to some extent. Yeah.
Yeah, it's really interesting how strong the data that you use is on these kind of problems, right? So if you,
Yeah.
in this case, like usually it's like, oh, throw as much data as you can at the problem, it's going to solve everything. But in this case, it's actually a bit surprising that it's not about the quantity of the data, it's also about the quality of the data. And the fact that you did this curation kind of is one of the things that made it work as good as it did.
Yeah. Exactly.
Did you have any unexpected results or findings, something that you kind of weren't expecting and popped up in the results?
Um. Well. Um. In our internal demo, it actually looks surprisingly good. So I think that's a surprise that we can generate 3D assets in such a short time. But the most surprising finding is what I've just mentioned, like because like the two parts of our model are trained completely separately. So for the second part, which is the 3D reconstruction part, we use kind of renderings from ground truth 3D asset. So when we train the second part of the model, it has no knowledge about um, the multiple views generated by 2D diffusion model that it will see in the test time. So these two parts are completely disconnected. And we actually do no data augmentation for the second part, which is the 3D reconstruction part. So it surprises me that so like because we don't do data augmentation, all the input views during training are always perfectly consistent because we're using ground truth 3D data. And what we expect is that if the input images have even the slightest 3D inconsistency, it will kind of generate some kind of 3D artifact like floaters, which is very common in NeRFs. But we actually don't see a lot of these kind of artifacts, and that means the images generated by the 2D diffusion model are actually very 3D consistent. This is actually the most surprising part to me. Yeah.
Yeah, I agree. I have to say, it was really surprising to me as well. And one of the things that I thought when I was reading the paper is, wait, like this is not trained in one go. Like this is trained separately. Have you experimented with training it like all together, or is it like too big?
Uh, No, we did not experiment with that because this already worked pretty well. And yeah, and because the how to say, because for the first part we're actually fine tuning an existing model, so we don't want to like
Mhm.
train it too hard to make it lose the original capability. And for the second part, it actually needs like a large amount of 3D data, and it takes a long time to train. We use like more than 100 A100 GPUs and train for a week or something. So
Wow.
they're actually a little bit incompatible during training. So doing it separately is like the easiest way to make it work, I guess.
Yeah, yeah, totally understandable. 100 GPUs is not something that everybody has in their, under their
Yeah,
desk and they can can experiment. But the
exactly.
reason I was asking is one of the points that you kind of touched on in the beginning, where you said that you start off with something that's totally 2D and has no 3D in it or like baked into it in any way. That I was thinking, well, maybe if you train it all together, then the 3D part is going to kind of back propagate into the 2D part and then they can inform each other. But yeah, this is just me thinking of future research problems.
Yeah. Actually, I want to mention there's another paper from Adobe, which was done by another intern. Um, we were interns in the same period. The name of the paper is called DMV3D. So the idea is that we still use this kind of transformer based model, but we kind of modify the architecture to make it a 3D diffusion model, and and then directly generate 3D assets that are guaranteed to be 3D consistent. But the problem in that is that because we want to incorporate this 3D structure, this kind of 3D constraint into the model, we cannot use the pre-trained 2D diffusion models out there. So there's this trade-off, like how do we, uh, the main problem is how do we enforce or kind of, um, maybe not enforce, but how do we make it like, make the model really 3D aware, instead of just like sparse set of, a set of sparse views, but how to make it the model really 3D aware, but we can still use the capability of a pre-trained 2D diffusion model. I think that's the key to the success of this kind of approach, and we don't have a very good idea about it yet.
Yeah, yeah. This touches back on all the challenges that we talk about in the introduction section, right? Like in 2D, you have the benefit of tons of data, everything labeled. You can train it. You have great backbones, amazing. In 3D, you don't have that, but in essence, the world is 3D, right? Every 2D example was originally, well, most of them at least, was originally either something 3D in the world or something synthesized in some computer somewhere. And it makes so much sense to have these kind of multimodal kind of approaches that find a good way to fuse between those two worlds that should live together. But yeah,
Yeah.
future work, which is a great bridge to the next part of the podcast, right? Conclusion and future work section. So, how do you see the impact of the paper going forward? And have there been any interesting paper that followed it?
Yeah. Um, I personally haven't seen any paper that directly extends the or is based on our paper. I think one of the reasons is that like we don't open, we don't release the code or the model of a paper because of some um, like fear of the company that that we have some like copyright issues or something like that. So it makes people difficult to kind of replicate. But because we're using the second part of model is based on another paper called large reconstruction model, there is like an open source implementation of that model, and that's released like maybe 1 week or 2 weeks ago. And there are some follow up works to the LRA paper, which, for example, uses um, uh, uh, which is doing single image to 3D reconstruction. And I think they basically swap the triplane for Gaussian splatting, which is a very hot thing right now. And
Yeah.
I don't remember exactly what the name of the paper is, but I think it's a hybrid of triplanes and um, Gaussian splatting. Because the difficulty of directly outputting Gaussian splatting is that the Gaussian splatting is basically unordered points, so they're kind of permutation invariant, and that's like a difficult thing to output directly from a feed-forward network. Yeah, I think there is follow-up works to the kind of the second part of the model, and we can kind of always uh, swap in different models for the second part because these two parts are completely separate. So, but for the entire 3D generation pipeline, I don't see like any follow-up works yet. But I have to say that there are some other methods that are, I wouldn't say follow-up, but they're concurrent to our methods. Another good example is called MV Dream. So they basically also fine-tune the 2D diffusion model to generate multiple views of an object, but they still use like techniques from papers like Dream Fusion to do test time optimization. So the good thing is that you don't really need to care if the model really the 2D diffusion model really generate 3D consistent images or not, because we will always kind of eliminate these small inconsistencies during during the optimization procedure. But the downside is it requires like longer time to generate one asset. But I think people have tried different representations or stuff like that and techniques to kind of, I think it can be reduced to 2 minutes for optimization. Yeah, I think, and also there's also this kind of product from a company called Luma. And I think the name of the product is called Genie, which kind of generates 3D objects in seconds, and you can also find kind of refine it with like 2 minutes or 10 minutes or something like that. So I think the kind of the seconds part is using a feed-forward model, and the minutes part is using an optimization procedure. Yeah.
Yeah. I mean, this is like for early PhD students that are kind of trying to figure out what problems to work on. I think this space is super interesting and super hot right now. I think mostly because it has so many real world applications, and like companies and startups are they want to be active in this space because you see what's going on in 2D image generation, which is it's already exploded. Like everybody wants to do something to generate. My 10-year-old son is generating images for his D&D class, right? So think
Yeah.
about like him having his own 3D avatar of his dragonborn barbarian, and not just an image that he can use that in, I don't know, some game, like some online gaming platform. That's just, it sounds like science fiction, but it looks like, yeah, we're almost there. And it seems like the field, I know from my point of view, will kind of branch out into two directions. Like one direction is how do we make it faster, and the other one is how do we make it more, aesthetically and visually pleasing, get the meshes right and the textures right, and then like there's a whole bunch of problems around those spaces that it would be
Yeah.
really interesting to explore.
Yeah.
All right, super fascinating space to work on. And we're getting to my favorite part of the podcast. What did reviewer two say? So please share some insightful comments you had in the review process.
Yeah. So the most critical reviewer um, uh, points out that we don't have like kind of maybe fair comparison about some of the claims. For example, the Janus problem. Um, the thing is, like, as I said, it's very difficult to evaluate this kind of methods. So usually we always kind of encounter this kind of questions from reviewers, like how do we really know it's like is better than other methods? And we have, as I said, we have like uncurated results for like hundreds of prompts in the supplementary material, but I guess many reviewers just don't look at them. And um, the so yeah, for this kind of question, it's like we don't really know how to answer, because you can always say like we really need some numbers to quantify the improvement, but we don't have this kind of commonly accepted metric. And also there are some claims in our paper. For example, we claim our model to be less kind of prone to uh, kind of Janus problem, and also our model has like higher diversity than those optimization-based method like diffusion. And the reviewers also want us to kind of um, do more extensive evaluation in this part. So I guess evaluation is something that everyone really cares about, because if you look at recent progress of 3D generation, sometimes it's really hard to tell like if they're actually better. So, but I personally don't think that's a big problem, because uh, for now, I think what we aim to do is to to solve the problem in different aspects, so that some of the results of some of the methods, we have different properties, uh, obvious that is obviously different from the other methods. So yeah, I think the other comments by the reviewers are mostly encouraging, I guess. Oh,
Yeah.
I think there's one thing that is mentioned by reviewer is the resolution problem, because we divide the single image canvas into quadrants. So inevitably we have the resolution of the generated views. So because our aim is to show that this kind of feed-forward pipeline can work, so we don't pay particular attention to the resolution of the generated views. But there are some other works like MVDream I have mentioned that kind of generate multiple views of the same object in full resolution.
Mm-hmm.
And that can be, if that is fine-tuned well, so that it generates like really 3D consistent images, it can be directly swapped into a pipeline to have like a higher resolution texture, for example. Yes.
Yeah, this could really influence the 3D output, right? If I look at the results, you can really see the grid structure that kind of is characterized with this kind of, as you go down in resolution, the voxels, the pixels, they become, bigger and more dominant. And if you have like higher resolution, you're going to be able to have better reconstruction of fine details and stuff like that. Obviously, it comes at a cost of some computational overhead and all those kind of things. But I do want
I think
to,
this is, yeah,
yeah,
sorry.
go
I
on.
think this is actually another problem, because what you mentioned is the resolution of the triplane, I think.
Right.
Because that's actually another like big problem, is that because we want to do feed-forward generation of a NeRF, and a NeRF is basically a volumetric rendering uh, model. So it has like we need to generate like information, generate kind of an asset that has information at every 3D point. And we use the triplane because it's like relatively efficient compared to like 3D voxels. But it's if we want high resolution, we still need to scale up the triplane, and that will have like a like that will kind of maybe have some problem during the training, like memory constraint or something like that. So these two
Yeah,
parts both have like resolution problems, and yeah,
yeah, and maybe that's something interesting to look at, right? Like, how can we compromise less in the resolution, but still overcome the computational overhead?
yeah,
Going back to what you said before, I think the evaluation part is a valid point from the reviewers, right? Like,
yeah,
it's valid all the time. Like, most papers, some reviewer would ask, "Oh, you didn't run on this data set or on that data set." But in this case, it's not about that, right? It's about, well, the evaluation. It's hard to evaluate, and how do we figure out a good way to evaluate that? Now, obviously, you can, ask a bunch of people what they like best, but these kind of things are they're more kind of, I don't know. To me, they feel social sciencey, and
mm,
like I feel like as a community, we don't really know how to do that very well in such a way that would actually tell us something. But maybe we don't need to, right? Like eventually, if it will make its way out to some product or some open source platform,
mm,
people would just vote for it in the fact that they
yeah,
will use it or not use it, right? So
yeah,
that would be the best metric. But it is, I think it is an interesting avenue to explore as researchers, right? Like there's a
yeah,
bunch of geometric properties that you could look into, like if there's some inconsistencies, there might be some bumps and stuff, right? So there might
hmm,
be like interesting research avenues as to evaluation, but definitely outside the scope of this work.
hmm.
Yeah, excellent. So is there anything you want to add that we haven't covered?
Um, not that come to my mind immediately. So, yeah,
Yeah, okay. So I think it's time to wrap up. All
yeah.
right. Okay, so
Thank you so much for
yeah,
having me today. Yeah.
thank you very much for being a part of the podcast. And until
Uh,
next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.